Hi, everyone. Welcome to 114th Stanford MedAI Group Exchange session. This week, we have Aimon Rahman from Johns Hopkins University here with us to talk about her work on ambiguous medical image segmentation using diffusion models. Aimon is a third-year PhD student at the Department of Electrical and Computer Engineering at Johns Hopkins University. Her research lies at the intersection of computer vision and medical image analysis, with the focus on developing deep learning techniques to make healthcare more affordable and accessible globally. Her specific research interests include 2D and 3D segmentation, generative networks, representation learning, and addressing bias and ambiguity in medical image problems. Aimon, thank you very much for joining us today. Before we start, do you have any preference on how you would like to take questions?
I guess I don't have any preference. You are okay to interrupt me.
Okay.
Yeah.
Okay, then let's try to make the session as interactive as possible. And without further ado, let me hand it over to Aimon.
All right, let me share my screen. Can you see my screen?
Yes, we can.
Okay. So, hi everyone. So today we're going to talk about ambiguous medical image segmentation using diffusion models. So let's talk about the motivation first, what we're trying to do here. So if you look into any natural image, right, you can see this is dog and it's a segmentation mask of a dog. And this is cat and it's a mask of a cat. And there's no debate about it. Like almost everyone will agree that it's kind of an accurate mask for a dog, or this is an accurate mask for a cat. So like I said, there's no like ambiguity in this case. But when it comes to medical images, the issue here is there could be some debate about the length and extent of lesions. So for example, we can see a CT scan of lungs, and then you can see four different raters have four different rating for the same lesion. So there are ambiguity in this case. So most of the models that we see, most of the segmentation model that we see right now, they don't have the capability of generating multiple segmentation masks per image. So they are mostly developed for single segmentation tasks. That means you just pass an input image and then you get a segmentation mask for that particular input image. So these models are deterministic and they are developed to imitate one individual, then like imitating a group of different doctors. So ultimately, the goal is to develop a segmentation model that can be probabilistic. So meaning for one single image, you should be able to generate multiple masks, but that should be realistic as well. So in this case, you can see we have a lot of, so for this particular image, you have two different masks, which are blanks, and then you have some segmentation masks for the same image as well. So there are some ambiguity, and then different doctors are rating it differently. We just need a model that can generate all these different segmentation masks, but it has to be realistic how a group of doctors would interpret it. So basically, this is the end goal of the project, to have a probabilistic segmentation model. To sum up the motivation, so we need collective insight. So we know that a group of experts, it has always proven to outperform individual based diagnosis. And it is a traditional practice as well. So like utilizing the aptitude of multiple doctors are actually part of clinical tradition. So in clinical cases, they have case conferences, specialist consultation, and tumor boards where they have multiple experts coming up with a solution. So we just want to use that in our deep learning pipeline. And then also some flexibility. For example, we know that deterministic models are like super confident. So even if it's uncertain about something, so it will just choose the most likely hypothesis, so which can be suboptimal in that case. So we just want to have room for some flexibility, like have different segmentation masks and let the people who use the particular model decide. Okay, so let's talk about some of the background of the existing probabilistic network. So So rather than talking about any specific one, I'll just talk about in general how the existing probabilistic network works. So at the heart of these network, you have like segmentation backbone, right? Which can be UNet or any other segmentation network. So this segmentation network can segment an image, and you pass it. It works like just your normal segmentation network. Like you pass an image and you get a segmentation mask. But we want multiple segmentation masks per image. So how do we get that stochastic output? So what we can do is we can sample some latent variable Z and inject it into the network so that it can produce multiple segmentation masks. So in this case, the way we can get this latent variable is through a network, which is going to be a prior net. So the prior net is conditioned on this particular input. And then once you pass an input, you sample a latent variable Z, you inject it to your segmentation network, you get some output. And then you keep doing it until like you get like n number of samples. So this is how the inference work, right? But during the training, you have a posterior net, which is another encoder that models a distribution, and you pass your input image as well as the ground truths. So that encoder models the distribution given an input image, what could be your segmentation mask, and then you minimize the distance between that posterior net and this prior net. So the reason why you do it is because so that your prior net knows how to like model the distribution of like the probable segmentation mask. So this is basically your conditional variation encoder based approach for generating probabilistic mask. So the issue here is your stochasticity actually depends on the latent variable Z here, right? So that's the only way you can generate stochasticity. You can get the stochasticity. So what happens is if you sometimes since you just have this you just inject it into highest resolution, you might not get as diverse examples. It highly depends on the Z that you just sampled. So sometimes you can get like noisy output, and then also it depends on the complexity of your prior net. So if it's not super complex, then you'll probably get diverse samples, but not realistic ones. That means it doesn't match anything from the original Docker samples, but you might get some diversity. So these are the problem that you might face if you don't have if you don't have complex prior encoders. And then there is an issue with evaluation metrics. So in this kind of network, the way you evaluate is through by seeing how the two distribution matches, like your ground truth distribution with your generated distribution, like the segmentation mask that you just produced. So this is the generalized energy distance, which where like D is 1 minus IOU, where S is your generated samples, and then Y is your ground truth. And here, these are your two independent sample for the same image. And then this is the two independent ground truths from, these are two independent ground truths. So in this case, the lower the energy distance is, it's better. So that means they are like closer in distribution. So we found a problem with GAD metric. That is, thing is, it might not always produce like it's not a very optimal evaluation metric. So it seems to reward if it has a higher diversity in the segmentation mask. So in one case is this one where you can see these are the ground truths. You have an input image and you have some blanks, and then you have two segmentation masks here. So even though in this case, you can kind of see that these are better segmentation, and in this case, you have like a lot of blanks here. So GED is lower for this one and then higher for this one, even though you have better matches. And then better number, like, because in this case you have 2 blanks, and in this case you have 2 blanks, but here the blanks are more often. So it is not a proper evaluation metric, or it's not a complete evaluation metric for the ambiguous segmentations. So here's the challenges. So what we need is an inherently stochastic network, both in training and then sampling process. And next we want multiple annotation for the dataset, which can be kind of expensive. So, and then we need a better evaluation metric so that it can be clinically relevant, and also we can properly evaluate the model. So, okay, so let's talk about the methods. So here we use diffusion models because the training and the test, like inference process, are both stochastic in nature. So let's talk about how we just train for the segmentation network, right? So in diffusion process, we just take an image, add noise to it, and then for the forward diffusion, and then for reverse diffusion, we just remove the noise. And yeah, so that's how then we could get a new image, right? So in terms of segmentation mask, what we're supposed to do is we have, instead of some image, it should be segmentation mask. And then we add segmentation noise in the forward process and then just denoise it. But it cannot be some random segmentation mask. It has to have some prior information, which is going to be your input slice, right? So in this case, we concatenate that input slice to the segmentation mask that we're supposed to denoise. So, and then we just train the regular diffusion network. So during inference, it's even more simpler. It's just how we do it for the normal diffusion, which is you just sample a random noise from a normal distribution, and then you just iteratively denoise it to get the image back. So in this case, you just have to attach the original image as well. Then you get the then you get the segmentation mask. So even before doing any of the other things, if you change each time you do the sampling, if you change the segmentation, if you change the noise, you get a small variation in the segmentation mask itself. So that itself proves that there is a stochastic element in diffusion model, which we can use we can use to generate like probabilistic segmentations. So next, what we do is we have ambiguity modeling network. What we do here is, which is basically a Gaussian encoder. So where we pass our CT scan, as well as some plain image, some segmentation mask, and then model that distribution. And then for the same step, we pass that segmentation, so pass that image as well as the output of the diffusion model for that particular step, and then you pass it to this another Gaussian encoder. And then you calculate the scale divergence loss. You try to minimize the scale divergence loss between these two. And during your diffusion during the training of the diffusion model, you have that MSE loss, which is for noise prediction. So you just add these particular KL divergence loss with that, and then you train your network. During inference, you don't have to do anything else. You just have to pass this particular image, and then you add the noise, and you denoise it to get a mask, and then you again sample from the Gaussian noise. You do it how many times you want, and then you get different segmentation output. So one question that I get more often, which I'm going to just clear it right now, it's during training, during each forward process. So the way we process this is we just take one segmentation mask per image randomly. So during the whole training, the network actually sees all the different segmentation masks per image. So
sorry, I'm a little bit confused here. So are you feeding the full image, or are you feeding the patch of the image?
Where?
Are you feeding the full city, or you are only feeding a single patch from the city?
Yes, single patch from the city. Yeah.
How did you identify the patch?
So it's already processed. So it's from a LIDC IDRI
No, I understand, but
dataset.
don't you think like
Yeah.
that is the primary difficulty to identify the proper patch for segmentation, like identifying the location of the tumor? Because once you identify the location of the tumor, then there can be a lot of different techniques for segmentation, right? But why
No,
don't
so
you start
yeah,
with the full image itself?
I don't think that, I mean, that's just you're passing a huge image that can have
Right,
some segmentation mask at some location, right?
right.
Tumor at some location. In those cases, if you just like, you take a big CT scan, you like crop it, patch it, and you pass it to the model, wherever it will see the tumor, right? It will just segment on that part.
So
And the
during the
part,
inference, you are feeding all the patches from the images, right? Or
yeah,
only the
yeah, yeah.
patch which has tumor?
No, all the patches.
Okay, okay, got it. Okay.
So it can basically generate a patch like with an output with no mask in it.
Yeah, right.
Yeah, if it
You
sees a
can
patch.
also do
Okay.
that.
Okay.
Because
Yes.
in the image you are only showing the patches with the tumor, so that's
Yeah,
why
yeah.
I was not sure like if you are feeding all the patches.
Okay. Yeah. No, so this is just for CT, but then we have for like ultrasound, which is gonna be the whole slides. And then for something else like MRI, which is also patches. For MRI, we also pass just the patches, but yeah, it depends. So for ultrasound, we do send the whole slide. So okay, so for the data set, in this case, we use LIDC, so which is a lung CT scan from 1,010 subjects with the manual annotation from 4 domain expert. So, so that means we have 4 segmentation masks per image in this case. And then we have bone surface, which is a private data set for ultrasound. So it's for bone segmentation. Bone surface can be, it's just a curved linear segmentation. So it's a thin line. So ultrasound can be noisy, so there are some ambiguity there. So in this particular data set, we have one expert and 3 novice user to do the segmentation. And then we have MSMRI, which is multiple sclerosis lesion segmentation. So here we have like 84 MRI scans from 5 subjects, but then we have segmentation masks, 2 segmentation masks per slice, because we have one with 4 years of experience and another with 10 years of experience. So these are the data set that we used. So then we have the proposed CI score, which is a method for evaluation. So for the CI score, we want to make this evaluation as clinically relevant as possible. So first thing is combined sensitivity. So the reason why we have in clinical setting, why do we have so many, like, why do we need so many segmentation masks? Because we want to cover all the bases. We don't want to like miss any pixel that has lesion in it, but none of the radiologists say there's a lesion in there. So we don't want that. And so we don't want that. And that's why in clinical setting, it usually works better when you have multiple rater grading a lesion, so that you don't have any false negative. So we're trying to emulate that by combining this sensitivity, which is we just combine all the ground truth mask, and then we can combine all the predicted mask, and then we calculate the sensitivity. That's one aspect of the CI score. And then the second aspect is the maximum dice matching, so which calculates the maximum dice score between the individual prediction and then all the ground truth. So which is something, so the idea is if you have a stochastic network, it might just generate some random mask, which actually a doctor will never generate, like never annotate, right? So we don't want that. We want to see whether these mask actually corresponds to a real doctor or not. So that's what we do with dice matching, where you take one segmentation mask, and then you just compare it with the best dice score that you have, and you do it for all of the generated ones and so on. And then you get the maximum dice score. And then finally, you have the diversity agreement. So first you need to have some good diversity. Of course, it shouldn't be for diversity's sake, but it should mean it should have the same characteristics as the ground truth. So I'll show you one example. So for example, in this case, right, you have two of them are completely blank, and then you have two of them with some segmentation mask in it. So the minimum diversity is between these two. They both agrees that there is no lesion here, and then maximum could be these two, right? These are the maximum diversity. So we calculate these numbers between two of them, and we get the maximum and the minimum, and we get that diversity agreement. So ultimately, the final score is just a harmonic mean of all of these numbers. So result-wise, we see improvement in terms of CI score and then dice matching when we use diffusion-based model. In case of GED, it's on par with the other models, but yeah. So the diffusion-based model performs well on dice max for all the other data sets, so for LIDC and then ultrasound and then MRIs.
I have a question here. So
Yeah.
how many masks you would be generating? But like would that affect
Oh, yeah.
your evaluation criteria? Like if you're generating too many masks
Yeah. So in this case, we did 16 masks.
per patch.
Yeah. So per patch, we have 16 masks. In our like for ground truth, we have 4 masks for LIDC, for 4 masks for bone segmentation, and then for this one, we have 2 masks. But for the network, we generated 16 masks per patch.
And if you increase or decrease the number of masks generated, would that affect?
Yeah, of course it would. So yeah. So yeah, so that obviously impacts the result. So I think after 16, then we didn't see much of the differences. So that's why we chose 16.
So up to 16, your numbers were improving, and beyond 16, they're kind of static.
Yeah, it's static, yeah.
Okay.
After that, it's kind of like all of the segmentation masks are kind of same or similar at some point. Yeah.
Yeah.
So we did it for all the other baseline. For that as well, we have 16 masks per image. So these are some qualitative results in that case. So you have some input image, and these are the results for LIDC. So some of them, so for example, these have mostly blank mask, but just one of them has annotations. And this is like more of a comparison with the other methods. So as you can see that, so in some cases, like the CVA-based method, you can see there's lack of diversity in the generated mask. And one more thing is in this case, right, none of the doctors there was no blank mask. So this is completely wrong to have a complete blank mask here. And so the frequency of blank should also match in the generation as well. So how you have in your ground truth. So that, and then one more thing is, so sometimes you probably get like some disconnected mask as well, that once you sample your variable Z, that you can kind of see here or like here. Yeah, so these are the results for the ultrasound. These are the ground truth for the ultrasounds. And these are the MRI results. So for MRI, yeah, so that it's yeah, so for MRI as well, it also depends on the quality of your latent variable Z. So that also changes. These are some more examples. These are some more qualitative examples that you can kind of see that, like some of the mask for a CVAE based method, you can see these are complete mask, but in some cases you'll get some of the incomplete mask as well. So yeah. So basically that's it. Thanks everyone. Is there any question?
Thank you very much, Aimon. Thank you for this interesting presentation. So before we move on to questions, let's give our speaker a virtual round of applause. And
Thank you.
the floor is open for questions.
I had a question about, in general, diffusion models have a certain time for inference, like they're.
Yeah.
So given that you are actually, generating not just one, you now have, I don't know, 16 masks.
Yeah.
How does that fit into the picture?
Yeah, that's true. That's a big problem with the diffusion models. That's the drawback, because the generation does take some time. Obviously, it's not as fast as the unit-based method. Yeah, that took some time. That's true.
Mm.
Because we use DDPM sampling process as well, because it has to be stochastic, so it did take some time.
And how much, like how large is the time? Like just to get an order of how many, is it minutes?
Okay, so yeah, so for each mask, it took like 45 seconds to generate. So now you have like 16 masks per image. So yeah.
Got it. Okay. Thanks.
Oh, I had a question about the training. So you used the 3 training data sets. So did you use the 3 training data set like all separately, or so is it right? Did you training the 3 training data set all separately? So like,
I'm sorry.
yeah, so you use the 3 training data set, which 3 training data set.
Yeah.
Yeah, and then well.
Oh yeah, separately. Yes, all of them are separately.
Okay, I see.
Mm-hmm. That's a 3 different model.
And on that note, okay, I think we have one question from the audience.
About the multiple sclerosis lesion segmentation. Often we see because it's longitudinal, right? So these lesions are sometimes they grow, sometimes they shrink, sometimes they even completely disappear. So like if you see medical image analysis last 5 to 10 years, or a lot of emphasis on longitudinal segmentation to capture the time point. So I would take multiple time points and then do the segmentation, right? So
Yeah.
do you have any thoughts about like bringing, how do you get the time component into the segmentation model?
Yeah, so I think that's more like a change detection kind of work, where you actually pass 2 images from different time and then see how what has changed and all, right. In this case, we just had, because for each patient we have like multiple like different time data, but each of them were segmented by 2 different annotators. So we actually used that. So we didn't consider like how does it change like in time. But yeah, that's more like in the change detection. There are some works on diffusion based change detection, like segmentation as well. So yeah.
Thank you.
Did you use?
Oh, G, please go ahead.
So did you use all the same patch size for the 3 different data set by any chance?
No, it can be different based on the data set.
Okay, I see. Yeah.
For all 3 types of the data set, form is saturated at 16 masks, or is it like different? Because I'm just trying to understand, like, how is there
Yeah.
connection between what type of modality and what type of lesion there is, and how many masks are possible. Like some lesions have like just inherently more masks possible than others.
Yeah, so I think this is more empirical, but I think it's because of these masks, it depends on how many annotations you have per
Okay.
image, right? So and so maximum we had like 4. So I think if we had more than 4, then it won't
It would
saturate
have-
at 16. Yeah.
Yeah, that's I think a good point.
Have you compared this to other methods, such as the conventional UNet? And how well would it do against small images?
Oh, yeah. So just the UNet is only a deterministic network. So we did compare it with probabilistic UNet. So that is where we have multiple annotation from one UNet, right? So we did like hierarchical probabilistic UNet as well. And there's some other paper called PhySeg where they inject that stochasticity at every level. So we did compare with all that. And so this LIDC is pretty small data set. So it only had 1,000 samples. So it worked pretty well. Even the largest data set that we use is actually the MRI one, but LIDC only had 1,000 samples, like 1,010 samples in it.
Have you tried it on CT images as well?
Yeah, LIDC is a CT image.
Okay.
CT data set.
All right.
Yeah.
Yeah. I'm sorry. I meant
So-
MRI images.
Yeah, MRI as well. That MS
Okay.
multiple sclerosis is an MRI image.
Okay. Thanks.
Okay, so if we don't have any more questions, then let's thank our speaker again. And if we did have any, if anyone has any questions for the speaker, we can put them in touch. Thank you very much, Aimon. It was very interesting.
Thank you.